Section 11.4 is the comparison test, and we're in this long series of sections where we're trying to tell whether a series is convergent or divergent. So this is going to be another tool we can use. There are two comparison tests. The first one, just called the comparison test, or sometimes the direct comparison test, says suppose that the sum of a sub n and the sum of b sub n are series with positive terms. First part is if the sum of b sub n is convergent and a sub n is less than or equal to b sub n for all n, then the sum of a sub n is also convergent. So the idea here is if we have a sub n less than or equal to b sub n for all n, then b sub n is acting like sort of a bound for a sub n. So if the series b sub n is convergent, then that's going to ensure that the series a sub n, which is bounded by b sub n, for the a sub n terms is also going to converge. Next part, if the sum of b sub n is divergent and a sub n is less than or equal to b sub n for all n, then the sum of a sub n is also divergent. So kind of goes back to the same reasoning. We have positive terms, so when we're talking about the sum of b sub n being divergent, it's going to, like infinity presumably, and if we have all the a sub n terms greater than the b sub n terms and the sum of b sub n is divergent, then that is acting like kind of a lower bound for the sum of a sub n, which also has to be divergent. So that's the idea. A note here, if we have this relationship for n that's fairly large, but it's not working for m equals 1, n equals 2, n equals 3 even, something like that, it's okay to go ahead and use the comparison test. Example 1, determine whether the series is convergent or divergent. And then as usual, we need to show work or justification. We're not just going to answer it's convergent or it's divergent without any work. That wouldn't be sufficient. So here we have the sum of 1 over 3 to the n plus n. So what we've gone over most recently is the integral test, so just to speak to that, we could actually look at using the integral test, but we're going to get stuck when we try to do the integral part because that's not an easy integral to take. So anyway, just speaking to that is not really a possibility. Comparison test, the way this works is your a sub n is your given general term in your series, 1 over 3 to the n, that quantity plus n in this case. And then you need to find the b sub n, which is a comparable general term for that series. So you want to pick something that you think or suspect would kind of behave like the a sub n. So looking at this often involves finding what's dominant as n goes to infinity. So 3 to the n versus n, looking at that, 3 to the n is going to go to infinity much faster than n. If we reduce this denominator just to 3 to the n, then we'd actually get a series that we know a lot about. It would be geometric. So we can tell for sure if that thing converges or diverges. It looks like that 3 to the n as n goes to infinity is going to dominate. So for those reasons, we choose our b sub n as 1 over 3 to the n is a good choice. So it's geometric. Just to convince you, we could write it in kind of the form that is on your formula sheet or in the definition. As a sum from n equals 1 to infinity of 1/3 times 1/3 to the n minus 1. So is this convergent or divergent? If you look at the geometric series information on the formula sheet, our r is 1/3, and since the absolute value of 1/3 is less than 1, then our series is convergent. So our b sub n is convergent. That's similar to our a sub n. We're kind of thinking that maybe this thing might be convergent as well. Let's see. So the inequality here, I'm actually going to erase part of what's here. I'm going to go through it. I wrote down my a sub n and I wrote down my b sub n. And you need to make the comparison and see if which one's bigger than the other, and then you'll come back and see if the comparison test applies to your situation, given that 1 over 3 to the n is convergent. So looking at the inequality, a way you can think about it, you could plug in several n to see what's going on, or just looking in general, 3 to the n plus n versus 3 to the n is always going to be bigger. So I summarize this as just the 1, which is the same in each of these, divided by something bigger than this thing 3 to the n, so I just call it smaller. What would result when you do the division is overall number that's smaller as compared to the one that is our b sub n, which I denoted big. So doing the comparison can go step back up, that this would be the correct inequality. And then you have to see if this inequality is going to help us. So you have the formula sheet at your disposal, which I have kind of later in the notes here. It's right down here, just to skip ahead. So this would tell you in the convergent column that if your b sub n, its sum converges, then you need to have the inequality going in this direction, which we have. So it is going to be convergent, but if you just think about it as well, that if we have our bound with our b sub n and it's convergent, then that's going to mean that with our positive a sub n, that series is going to converge as well. So it also just makes sense. That's our conclusion. It's good to write what test overall you're using, especially if you didn't mention it before this. So this was by the comparison test. And then also, what is your b sub n that you were using, or what is the series for which you're comparing to. So that was example 1a. I have a little information here just speaking to what if you chose a different b sub n, like maybe you didn't recognize the dominant term thing, and what if you just chose 1 over n, and just also to kind of see what can happen when it doesn't work. Well, you do your comparison the same way, and then I actually do it this way, where I figure out my comparison that it's small, big, so then the less than goes up. That when we're talking about 1 over n, its series is the harmonic series, which is divergent. So what this is saying is we have a series with a positive term here that's divergent, so it's going to infinity. That's what's happening here. And the series that we care about, we want to know if it's divergent or convergent, is smaller than that. So it could be some smaller infinity, or maybe it is convergent to some value. You just can't tell. So this is an example where the comparison is not useful, and the convergence or the comparison test doesn't say anything about the convergence or divergence of our series. So on this formula sheet that we snuck ahead to, here it is, the information. I don't have the columns here because it's the very top, but this one says series, this one says convergent, this one says divergent, so this one satisfied the requirements here. And then here's a reminder here that the a sub n and the b sub n terms have to be positive in order to use the comparison test.